No, there we go. Okay, because sometimes people want to review the lessons and whatever. Mike said something about whatever I was writing and I didn't catch it all or whatever. So I perhaps should have done that at the very beginning. I forgot to do it. If I forget in the future, I start blah, 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 and I forget, say, Mike, record, so we can, have access to the talks. One question, Ashley.
Mike Ashley doesn't look old enough to have done all of that.
I know, right?
Do you still get carded when you go to a bar, Ashley?
What?
Do you still get carded when you go to a bar to order a glass of wine or beer?
Yeah.
I do.
I imagine it's in some ways when you're young. I mean, you're young, but you're old enough to do that stuff, and you get carded. You're like, oh, come on. But when you're my age, it's if you get carded, you're like, you feel so good. It's like,
yeah.
They're usually doing it to be nice, but still,
yeah.
It's like,
well, the thing that really gets me is when my friends who are younger don't get carded and I do. But
right, it all depends on how how you age or whatever. So but I do have one question. So do you know by any chance Ken Stafford, Colonel Stafford at WPI? He does robotic stuff now. He's retired, but he used to run the Air Force ROTC.
I've heard about him, but I haven't met him yet.
Oh, okay. So he's well, we call him the Colonel. The reason he still runs. My knees are gone, so I can't run anymore. But I probably ran at some total of 8,000 miles with him over the decade. We used to run marathons together and whatever. And of course, when you run, you talk. So I heard every Air Force story that he was allowed to say. I didn't hear the secret stuff, but so if you meet the Colonel Ken Stafford, just say hello for me. He's around, but he when he retired from the Air Force, he stayed around at WPI and he does robot stuff. So anyway.
Yeah, that's awesome. No, we were talking about trying to reach out to him because we want to reach out to the whole Air Force community. There's not a ton of us, so.
Right. Okay. Anyway, so all right. Well, thank you for that. That was enlightening and interesting. Everybody has quite an array of experiences and what have you, and here we are studying the same thing, system dynamics. My background, we'll get to it as we go along, like how come I'm here and what do I do and what have you, rather than me just telling you now. You'll see it's kind of integrated in with some of the talks that I'm going to be given now and in the future. The syllabus and all that stuff, we'll get to that in just a minute. But before I do that, I wanted to say it's kind of amazing. People ask me, why did you become a professor? Why don't you go to industry? You can earn more money in industry and whatever. And it's like, yeah, but being a prof, I can do whatever the hell I want, which is it's quite a nice thing to be able to. I mean, I do have to show up and teach classes to collect a paycheck. I do have to do that, but beyond that, most people don't even know what I do. I mean, the provost has no idea. Well, he knows who I am, but he doesn't know what I do. He has no idea. I'm not entirely sure my department head knows what I do. He knows broadly what I do. I could be teaching, voodoo rockets going to Mars, and they would have no idea. So it's kind of nice to be able to do whatever you want to do. So that said, what I'm getting to is a typical graduate class here or elsewhere lasts 14 weeks, 15 if you get a fall break or a spring break in there. The number of lectures, often is twice a week for 14 weeks, 28 lectures. What I've kind of said is, why don't we go once a week and we'll go 14, 15, 13. We can go as long as you want. At some point, I'm satisfied that I've given you, quote unquote, SD 550, whatever the heck that means, an introduction to system dynamics. Like at some point, I'll say, okay, if we stopped now, I would be confident that you've had an intro to the field. But there's all this other stuff we can still do, and I'm happy to do it if you want me to. On the other hand, you might be saying, Uncle, at that point, no mas, then that's fine as well. So we're not bound. I have to give you guys a grade December something. I don't even know what it is off the top of my head. I could look it up, I suppose. So between now and then, we can do whatever the heck we want. I mean, I said Monday nights at 6. There's nothing that says we can't meet at, Saturday at 3 a.m. I'm not advocating that, but I'm saying if we did that, nobody would know or care. So we can kind of do as a little group here, whatever we want, meet as many times as you want, when you want. If you want to skip something, it's Labor Day. We don't want to meet on whatever. We are very flexible and we can do what we want to do. So just so that's on the table, and don't feel afraid to tell me I got to travel somewhere. I'd rather not meet. I mean, I could watch the tape, but who else doesn't want to meet? And somebody else might say, I got a lot on my plate too. Let's just skip next week. We can do that. So much more flexible than a more rigid, structured, class. Having said that, you'll learn all the stuff, but it's just a little bit of an easier way of doing things. And unlike undergraduates, where you've got to, if you turn your back, they're short sheeting your bed or doing who knows what. You guys are here because you want to be here. Right. So that makes a great deal of difference, when you got folks who are motivated, full grown adults who are motivated and whatever. So we can be quite flexible. So did we lose? Are we back?
Yeah, I think
the recording just stopped for a minute.
I think it was your connection that went out because the recording stopped, and then as soon as you came back, the recording started again.
Oh,
must have been your connection, Mike, because your video screen was freezing up before that.
Oh, it was. Oh, okay. I actually, I actually got a new internet service, like literally last week. We cut the cord from Comcast. Progress. And we got our town has its own electric company, and they put in fiber optic, whatever. So so there might be some gremlins in here that because it's a new system, but so if there's gremlins, we'll fix it going forward. But for now, bear with me if there's something that I'm unaware of. Anyway, so we can be flexible. As long story short was what I was trying to get at. Okay, so having said that, and it's got some weird virtual background thing showing up here on my. Let me see if I can. Okay, I got rid of that. Sometimes Zoom hasn't. It just updated my Zoom, and there's a new version, and there's new features that suddenly appear. It's like I don't know what's happening. Okay, so any questions before we start sort of plunging forward here at this point?
Are you going to send us the syllabus such that it is just to kind of a list of things?
So, okay. Yeah. So we're about to go to the syllabus. In fact, let me do that real quickly here. Can everybody see the syllabus? Is that okay? Everybody can see?
Yeah.
Okay. Okay.
Yeah.
Okay. Good. Thank you. So, yeah. So if, like Suzanne, you're just sitting in the course. So you're not enrolled, so
Right.
you won't have access to this.
Mhm.
But I could, like copy and PDF it and send it to you.
Okay.
So that's certainly possible. Yeah. Okay. So when I do my courses, particularly graduate courses, what I do is I really load them with stuff, the syllabi, I should say. So this thing is you look at all the line items and videos and stuff, and often this freaks people out. They're going like, oh my God, how am I going to possibly? And that's not the point. The point is not to say you're going to do all of this stuff or you won't pass or something. It's just that a lot of times people will get into it. They'll like really enjoy what we're doing. And it's like, all right, here's a bunch of famous stuff and stuff you should read. It's not going to be required for the class, but if you want more, here it is. You don't have to search it up somewhere. Here's a bunch of famous papers and whatever, just right here for the taking. So if you want them, here they are. If you don't care, don't worry about it. Okay. So for example, Najla was talking about sort of a sustainable cities climate adaptation in city stuff. Well, here's some urban dynamics, city SD modeling stuff. So she might want to take a deeper plunge than somebody else in an urban modeling context, so on and so forth. Okay. So here's kind of the standard, everybody who does this sort of course does it similarly, but differently, same, but different. But here's kind of an outline about what we're going to do. We're going to start by explaining what the heck system dynamics is, okay? And then give a lot of the history of the field and an overview of the field. And sometimes someone might say, geez, this is not a history class. Why are you telling me? But along the way, we'll find out a lot of not just the oral history of the field, but we'll see some famous models that are well known in our field. And you should be familiar with these models if you're, studying system dynamics at the graduate level. So there's a whole bunch of background here on that. Then we'll get into modeling. Why do we model? This is a modeling class. Why do we do that? What advantages are there to modeling? We model complex nonlinear feedback systems. So what are their characteristics? Conceptualization. If you want to build a model, how do you go about doing it? I'm talking about an original model. Well, you have to sort of conceptualize the model, basically decide what's in the model and what's not in the model. We're not trying to build a digital twin of the real world. We're trying to model a problem from a systems perspective, not model the system. So we need a problem statement, and in light of the problem to which the model will be devoted, can we conceive or conceptualize the important stuff that should go into our model, and how might you go about doing that? We'll talk about reference mode. So what we do with a system dynamics intervention typically is start by asking the client, could be if you're modeling for yourself, you're the client, but you're often the modeler and somebody else has the problem. You say, what's the problem? What is motivating the modeling effort? You might not be a problem, might be something you're curious about or don't understand well. Okay, what is it? In plain English, in one sentence, tell me what it is. It's almost never possible for somebody to tell you in one sentence on the first try, but you try to get them to focus, narrow. What is the problem or the issue? And boil it down to something straightforward. Once you know that, we make a picture out of it, a dynamic picture, and we call that a reference mode. And the base run of a system dynamics model should look like and mimic the reference mode. And if it does that, we have an explanation for why the problem is occurring or why the curiosity is occurring. Okay, I'm not saying the explanation, an explanation. Okay, and then you have a tool for running what if experiments. Well, okay, what if we change this? What if we change that? What we're trying to do is take an airplane. It's not always an airplane, but imagine an airplane, which is a complex system, complex nonlinear feedback system. And that airplane is not flying well. We would like it to fly faster or higher or more fuel efficiently. See, I have an Air Force officer in here, so we're going with the airplane. Or carry more cargo or whatever the case may be. So you want to redesign, you're not gonna throw the plane away. You want to redesign it so that it performs better, whatever better means. So in addition to a problem statement, we try to ask people or get the client to tell us, well, what does fixed or solved mean? Or what does better mean? And it's not always obvious, right? How do you make your city better? I want more open space and parks. Well, not if you're a real estate developer. A real estate developer might say, that's not my definition of better, or your definition of better is, I want more ballet and opera. And people who can't stand that stuff, they're going to say, that's not my definition of better. So it's not always obvious what the problem is, and it's not always obvious what the solution is. So, and it's often a multi-attribute definition of better, right? What does a good spouse, what are the attributes of a good spouse? Beautiful or handsome, tall, rich, funny, comes from a good family, whatever the laundry list is, it's multi-attribute, right? So it's tricky business to do that. So we try and start talking about how one might get people to tell you what the problem is and make a picture out of it, the reference mode, tell you what better means or solved means, and then make that formal, because we want the model to mimic that stuff. What causes dynamics? What causes change over time? What causes the problem? What causes the reference mode? Those are stocks and flows from a system dynamics point of view. Bathtubs and faucets. They might say that sounds like childish or whatever. It's simplified conceptually by design, but if you want to do math talk, we simulate nonlinear ordinary differential equations. So we're going to do calculus. Now, a lot of people don't even realize that's what we're doing. At WPI, until COVID came around, we annually hosted DynamicQuest, which was fifth graders coming to WPI to show off their system dynamics models. And Jay Forrester would come and be sort of a judge or whatever, and we'd do a group model building exercise with them and give them blue ribbons and stuff. Well, these are fifth graders doing system dynamics. So they didn't realize they were simulating nonlinear ordinary differential equations, but that's what they were doing. So, so getting the math talk off to the right and off, we don't have to worry about that. It's stocks and flows, bathtubs and faucets cause dynamics, and you'll see what that means as we go along. But the bathtubs and the faucets, the stocks and the flows don't exist by themselves. They're part of feedback loops. Feedback is the transmission and return of information. Information on what? Information about the amount of stuff that's in the stocks or the bathtubs, the amount of water in the bathtubs, the amount of morale in the bathtubs, the amount of widgets and inventory in the bathtubs, whatever it is. Okay, so we look for stocks and flows and feedback loops. And so we talk about how do you do that? How do you map them out and what have you? I like to get students to see a little bit at the back of the envelope level what the computer is doing when it does whatever it does to solve our system dynamics models. So you don't have to have a degree in numerical analysis. We don't have to go that deep where we're writing Runge-Kutta algorithms and stuff. But you have to have a good understanding conceptually of what the machine is doing to solve these models. And then we say, okay, I get it. The machine can now do all that stuff very fast. It doesn't get tired and what have you. Along the way, we learn about the strengths and the weaknesses of system dynamics. When you see what the machine is doing and what constraints there are on what it can do, then sometimes we conclude that a particular problem is really not a system dynamics problem. You should really consider using a different tool. And I find our graduate students who are into system dynamics, they really want to do system dynamics. To them, every problem is a system dynamics problem, even when it's not. So we try and get people to say, sometimes you just got to say it's really not an SD problem, or I could do it with system dynamics, but it'd be clunky. It's really not designed for that particular use. You might consider a different tool, right? So, having the idea of a tool kit rather than I have one tool, it's a hammer and everything's a nail, that kind of thing, right? Then we're going to introduce the software, Stella. Stella stands for Structural Thinking Experimental Learning Laboratory with Animation. I believe that today it's the best system dynamics package that there is, which is why I've elected to use it. But there are plenty of other packages out there that are quite good. There's VenSim, there's PowerSim. there are people who will do system dynamics with Excel. There's one guy, Jim Duggan, does system dynamics with R. There's another person whose name escapes me. I haven't really met them, so I've just heard about them, but they do system dynamics in Python. You can use, if you're a MATLAB person, WPI, most of the kids do MATLAB. MATLAB has a simulation tool in it called Simulink. You could use Simulink. A friend of mine, fellow economist, Steve Keen, has his own package that he created called Minsky. And you could use Minsky to do all that. So there's how many packages or ways that I just cite there? Probably like 7 or 8 or something. And there's a lot I didn't cite. So you can do system dynamics all different ways. I choose to use Stella, and you'll see why as when we introduce it and go through the features and the things you can do, you'll see why I feel it's the best package, but that's just me. You can take whatever we learn here and do it any way you want if that's your thing. And then there's a bunch of stuff where we're going to start looking at best practice for building a system dynamics model. It's really easy to build a crappy system dynamics model. So it's really hard to build a good, insightful system dynamics model. So the software is accessible to pretty much everyone. And there are free versions of it. So you can get free versions of Stella. So you can just have at it with no training and build some gargantuan thing that, isn't good, but hey, you're doing system dynamics, I guess. That's not what we're trying to accomplish. We're trying to instill in people in the first class what we mean by a best practice in system dynamics. How do I go about my business such that when we're done, we're likely to have a decent model? There's a bell curve. There's some people who are super talented and build just these insightful things. And you're like, how did this person do this? It's like genius level. They can see what I can't see. There's other people, no matter what you tell them, no matter how you help them, they just can't do it. But everybody else, there's a bell curve. Most people are in the middle. Once they learn the best practice and so forth, they can do it and come up with a decent model. Okay. So we're trying to do that. So first order control, what is that? Why do we need it? What's Little's law? How do we do partial model testing? Why is that important? What is steady state error? How do we know we have it? And if we have it, how do we get rid of it? Stuff like that. You'll also find that we have a lot of what we call generic structures in system dynamics. There are different names for these things. They're called assemblies in Stella. They're called molecules in Vensim. Early on in Stella, they were called atoms of structure. It depends on the author. The different software companies name their things different things, so they're seen as separate. But the idea is, if you're building a model, you don't want to always reinvent the wheel. So I often give the example: if I was a client and you were a Python programmer, and I said I'll pay you to write me a program in Python to sort. I have 1 million names in my customer base: names, addresses, what the person purchased from me, whatever. And I'd like to be able to sort them this way, that way, whatever. Please write me that software program. Now you could open up a Python environment to, there's all these different Python environments where you can create your code, create and test your code, pick the one you like, and it's blank. And you could invent and figure out a sorting algorithm from scratch. No one does that. What does a veteran programmer do? They go to some place like GitHub and they search Python, shell sort or bubble sort or double bubble sort or whatever. And somebody's already done it. And they copy the code, they paste it in, and they modify it to fit their requirements. And if they're writing it up, they cite I got the base code from here, so you're not claiming you invented it. That's what everybody does. Nobody keeps reinventing the wheel every time, right? So we look for all sorts of generic structures, molecules, assemblies, and whatever first before we try and invent something on our own. So expectations, how do you formulate expectations? Well, people make decisions a lot of times not based on what is or what they think it is, but rather what they expect it to be in the future. Very important to be able to model that. Well, how do you model that? Well, somebody's already done it. Not saying you can't come up with a new twist on it, but rather than staring at a blank canvas, let's see what others have done. Let's look at some generic structures. More for the kids who are into engineering stuff, there's PID, proportional, integral, and derivative control. So when you have, this is classic, there's modern control theory and classical control theory and in robotics and electrical engineering. It's really in all of engineering these days. But the idea is you have a dynamic system and you want to control it, right? You want to keep it under control. Think of a thermostat controlling the temperature in a room, a guidance system on a missile, controlling it to the target, a cruise control on a car, something like that. Well, how do you do that? Well, traditionally in engineering, you use PID, proportional, integral, and derivative control. And particularly for the kids at Tech who are studying that stuff, I say, when we're doing this in system dynamics, we're doing PID. You didn't know it because I didn't call it that, but that's what we're doing. Okay. And it's a feedback system. Putting it all together, we'll start to notice that when you build big models, by first building little models and testing them until you're absolutely sure you understand how they behave. And then and only then do you hook it up to another small model to make a bigger model. What you don't do is say, oh my gosh, I got this great tool called System Dynamics. It's the silver bullet, the panacea, the thing I've always imagined and never knew what it was. And now I've discovered it. Eureka. And I want to solve world hunger. And as fast as you can move the mouse, you build this giant model that has all your ideas and whatever in it. And then you hit the go button and it blows up. Typically at this point, the student comes to me and says, can you help me? And I go, of course. Where do you need help? Well, I built a model, it's not working. Okay, show me. And they open it up and I'm like, there's this crazy bird's nest of every idea they've ever had is all in there. Now that's actually not bad. It's like, we're going to save that because that's brainstorming. You got your thoughts there, so don't delete that, but we're just going to take one little piece, open a clean new file, and we're going to work on this one little piece until we get that one little piece right. Then we're going to go back to your brainstorming file, pick another piece, test it, and then put it together. And getting people to be disciplined to do that. You say, well, that's common sense. People don't do that though. You got to imply discipline to your modeling. And when you do that, you have a better chance of at the end having a decent, insightful model. Okay, how do models behave? Well, this up here, when we're doing this stuff, we're going to be seeing just simple little behaviors, nothing dramatic. But the first sort of more dramatic behavior is oscillation. And that requires a more complicated model, and lots of systems go up and down. In my world of economics, economies go up and down. Business cycles, but lots and lots of systems go up and down. So why does that happen? Another more complicated time shape is S-shaped growth. So you get exponential growth at the beginning, but then it gives way to a negative loop or an equilibrium or stabilizing behavior. And why is that? Well, because systems typically have limits. Perhaps the universe, if we believe in the Big Bang Theory and it's expanding forever, rather than the big crunch where it stops expanding and starts going the other way. The Hubble constant is, determines how quickly this allegedly is happening, I guess. I'm not an astrophysicist, but other than maybe the universe, systems that grow or decline forever really don't exist. They have limits. They have floors and ceilings. And as soon as you introduce limiting factors into the equation, now we got behavior like S-shaped growth. Not only that, but that would be the first example of a situation where you have limiting factors. So we try and get people to understand when you're doing systems thinking, when you're getting the big picture, You're looking for stocks and flows and feedback loops, but you're also looking for limiting factors, that systems don't grow infinitely large, Jack and the Beanstalk stuff, or it grows to wherever, to the moon or whatever. And they often don't decline forever. They might stop at zero. Having negative people doesn't make a lot of sense, right? You might have no people, but negative, there's a floor, right? So then how do you model these floors and ceilings and what have you? Table functions are one way of doing that, so we'll look at that. Another one is overshoot and collapse. So if people are not mindful of limits to their systems, in my world, I'm a system dynamics person, but I'm also an economist first. So one of my first moves is I think of supply and demand when I'm, hearing about a problem. And then I also think about stocks and flows and feedback loops. Well, if you have more demand than you have supply, you can have overshoot and collapse. Okay. And then some more technical stuff. This is where we start to say, all right, if we get this far in the class, we've done a lot in an introductory class, but we're graduate students. So if we want to push on, we'll start doing some technical stuff about initializing system dynamics models and parameterizing them properly, and building more complex models, looking at more complex models. I have a lot of project management stuff in here because usually when I teach graduate students, they're working professionals at high-tech companies, and they're all working on projects. So, but we don't have to obsess about project management if you don't want, but that's a common one. Policy optimization. We've got a model and it looks like it's telling us we should lower tax rates. Well, what's the optimal tax rate? How far should I lower it? Well, there's techniques for that. That's optimization, policy optimization. Sensitivity analysis, Monte Carlo experiments. Well, okay, I got this insightful model. I followed all the stuff that Radzicki said is a best practice. I've optimized my policy. Here's, I'm going to tell, you were an aide de camp, Ashley, the admiral, or I'm going to tell somebody at a health insurance company, Suzanne, or you're going to tell the mayor in a city or what. What do you think you should do? What you don't want is your analysis to fall apart the second you change something a little bit, because you have a model. It's not real, right? It's your best educated guess as to how the system works. And you got this wonderful result, but the second you change something a little bit, now all your results fall apart. No good. You want your results to be robust, right? Well, Monte Carlo analysis helps us determine that. Okay, how robust are your results? Building confidence in system dynamics models, super important. A lot of times academics like me build mathematical edifices, mathematical artwork to publish in a journal that's peer reviewed, so we get the esteem of our peers. It goes in the historical record in a scholarly journal to be admired. Look at this brilliant mathematical contraption that Radzicki or whoever created. It doesn't do anything for the real, it doesn't make the economy better if it's an economics model in my world. It's just this mathematical edifice we've built to admire. Print it out, frame it in mahogany, put a light on it, hang it on your hallway, bow to it as you walk by at your brilliance. No good. In system dynamics, the whole point is to make the system better. You can throw the model away if you succeed in doing that. In order to make that happen, the people who are in charge, who have the authority to change things, to redesign the airplane, to cut taxes or to raise them, to hire people or let people go, or whatever the case may be, whatever you're recommending, they have to have confidence in the model and what you're telling them. Like, where are you coming up with this? A lot of times it's counterintuitive. So if they don't understand, or if you just say, well, the computer said to do it, they're not going to change things dramatically, counterintuitively because of that. So we talk a lot about building confidence in our models amongst ourselves and then amongst our clients, so they believe what the model's telling them and take it seriously. Part of that involves model documentation and presentation. It's quite mundane, boring even, but it's very important. We want to make sure that people can replicate our results. The worst thing you can do is come up with this brilliant insight, cold fusion or whatever it is, and nobody can replicate your results, right? In system dynamics, we take great pride in that most of our models, 90% of them or whatever in the literature, can be replicated exactly, right? That doesn't mean they're good models, but at least we're presenting ourselves scientifically to the scientific community, and they can, and others can replicate and then extend our results. So how do you document your model so that that's possible? And then finally, we try and get people to see, just to whet the appetite. In a first course, you can only get so far. But one of the ways we try and get people who didn't build the model with us, but they're often in positions of authority, to get them to see the insights from the model. We often find that turning the model into a game that's engaging, it might even be fun, but it's not a ha-ha, let's kill zombies game. It's a serious game, but it's engaging. People want to try hard, but they get the insight, they learn the insights on their own. You don't go into a conference room to the admirals or the bosses or whatever it is and just put 10 bullet points on the board. Here are the insights from the model, memorize them. I mean, that doesn't work. But we found that letting them play a game that is fairly sophisticated, so it doesn't come off as trivial, and it's engaging, they want to do well, and they're into it, and along the way, they're learning. They're trying to win, but in attempting to win and be serious about their decisions, they're learning. They're getting the insights from interacting with a dynamic, complex feedback system. And that's the best way we found heretofore in our field to help those who did not participate in the building of a model understand a model and begin using the model and getting the insights from the model and maybe actually changing the real system the way the analysis suggests. So that's a big, the whole thing of gaming is a whole area. We can't do justice to it in one section of an intro course, but we whet the appetite here. And hopefully you'll say, I want more about gaming, to have another course in gaming, something like that. Okay. So let me pause just right here and say to everybody's hanging in there. And I mean, it's just an overview of what we're going to do, but I just want to make sure we're good.
So we can take another course to gamify our models if we want to?
Yeah, Khalid Saeed teaches a class in that. It's an undergrad course, but graduate students can take it, and he gives you extra stuff to do. So yeah, and we should have one of those online at some point. All this is in process. There's so many hours in the day, But yes, right now you could take that. Khalid would do that. So, but yeah, so gaming is one of the last steps. You got to first build a good model and before you turn it into a game, right? But you could take the gaming stuff, at any time. All right. So, So I'm assuming everybody's cool with what I said. Everybody's, nobody's baffled or running for the exits. In terms of assignments, I've done this a lot of years in a lot of different ways. And I found, particularly when we got to do it online or in a hybrid situation, that, I didn't publish. I thought I had published these. Sorry. I guess it was my undergraduate class. Here will be the first assignment. Basically, I'm going to ask you to read an article, and then I'm going to ask you to play with a game, a system dynamics game. And then it's an assignment, but it's a quiz, and the quiz will ask you questions about the article and about the game. You have, what did I say here? 3 attempts to score. There's no time limit. You could have the article open and answering the questions. You can have the game open, answering the question. So we're not trying to trick you or make you memorize stuff. We're, just do it any way you want. Just, play the game carefully and read the article carefully. That's all we're trying to get you to do. Okay. So in terms of like, how are you graded or evaluated? That's what we're going to do. I haven't published this one yet. So, I mean, I can do that right now. And now it's published. Now you can see it. And you have unlimited time. You can have till December to do it. It doesn't matter to me when you do it. Different people have different schedules and whatever. So
How am I going to get this stuff, Mike?
yeah, well, therein lies, again, I guess I have to PDF it and send it to you. And then like the game,
It's in a-
there's a link to the game.
Yeah,
It's
I mean, as long as it's in electronic format and I can click on it and I can just create a folder with all these things.
yeah. I think most of the stuff is possible to do that way. There might be a this or a that, but most of it should be possible to do without Canvas.
Okay.
When you don't have access to Canvas. Okay. All right, so let's start off by talking about just what the heck is system dynamics. Some of us might have a little bit more of an idea of what that is relative to others. And let me start with something that I had to do for one of these parent day things or new student day. I can't remember. Some open house, I guess it was called. Don't worry about technology, but it's undergraduate stuff. But here's kind of the pitch that I was making to everybody, that there's one way of doing science is called atomism. And basically what you do is you take a piece of a complex system and study it in isolation from the rest of the system. So if you're doing a deep dive into this one little area. So if you're inventing, working as a chemist, making new molecules for new medicines, you're not worried about the marketing of the thing. You're not worried about the FDA approval of the thing. You're not worried about any politics behind the drug. Is it an orphan drug or controversial medicine or something? You're not worried about the economics of it, any of that stuff. All you are is you're in your lab coat with your Bunsen burner and your test tube, and whatever you do, you're doing the science hardcore, and the other stuff is just noise that's in the rest of the building. So that's atomism. You break off your little piece of the bigger system and you do a deep dive on it. And lots of advances in science, technology, human welfare have come from that particular way of doing things. And we're in my department, SSPS, which is where system dynamics is housed, we're really not trying to go after the student who's coming to WPI to just build robots. All they want to do is be in the lab making their robot or mixing their chemicals. They're the ones who come into my class and are like, yeah, I got to take some social science class and graduate. This one fit my schedule. What do I have to do? They don't care. They're so focused on whatever the techno thing is, and that's fine. No hard feelings. I get it. And that's not who we're really trying to reach with our programs. Rather, the opposite of atomism is holism. Okay. So this requires a systems approach, or looking at not only the pieces of the system, but how they're hooked together and how they interact with one another. So it's really an interdisciplinary approach to problem solving. And the so-called grand challenges that are out there, and there are a number of these lists of grand challenges. I got to just find my cursor that disappeared on me. It went somewhere here. Sorry. There it is. When I got multiple screens, I tend to lose my my cursor a lot. But here's one list of global grand challenges. Some of these might resonate. Sustainable cities, okay, climate change, global health, food, water, energy nexus, and the digitally transformed world. So these would be examples of nasty problems that are interdisciplinary in nature, dynamic in nature, and require a holistic approach. And this is not the only list of these things. I'm sure Ashley has some national security things that she could talk about and what have you. But what we're trying to say in this presentation to the kids is if you're interested in those sorts of problems, then you have to be able to see the big picture. Okay, you have to see how the pieces of the puzzle fit together as a system. Okay. So we also argue that solving society's grand challenges requires leadership. You see that's in bold strike in red. Leaders are doers. They can see the big picture, right? We argue that leaders are systems thinkers. And again, with a military example, at least I'm not sure about the Air Force, certainly in the Army, the lower levels, not the lowest level, but the lower levels are specs or specialists. Right, they're very narrowly focused on a subset of things, right? Whereas the highest level, the generals, are generalists. They have to see the big picture. They have to understand how the artillery interfaces with the quartermaster corps and the infantry, and and what have you, how the pieces fit together and work together. So we argue that they're systems thinkers. So leaders are systems thinkers. So one goal of the course, one reason for studying system dynamics is to get people to become, or at least beginning to be becoming systems thinkers. And, what does it mean to be a systems thinker? Well, to see all the parts, well, it's a little bit more than that, but that's as a beginning, we'll start there. So can we get you, using this tool we call system dynamics, can we get you to become a systems thinker? Okay. What else in terms of what we're trying to accomplish here? I have another deck of slides here. Let's see if we can talk about some things. So as we go along, we're going to talk about Jay Forrester here. There's a picture of Jay. Jay Forrester is the person who invented system dynamics. Jay passed away in 2016 at the age of 98. So he was born in 1918. Okay. And he has a whole laundry list of accomplishments that we'll talk about as we go along here prior to his creation of system dynamics. But as you'll see as we go along, all of the stuff he did prior to system dynamics kind of got melded together into what we call today system dynamics. So servo mechanisms, those are feedback systems. Whirlwind One, he was the leader of the team that created Whirlwind One, which is MIT's first general purpose digital computer. And as Jay likes to say, it wasn't the world's first general purpose digital computer. It was about the world's fifth general purpose digital computer, but it was the world's first general purpose digital computer that worked reliably. And after Whirlwind, he created, or he co-led the team, I should say, that created the SAGE air missile defense system for the United States, which was basically a bunch of Whirlwind computers linked together with radar stations. Today, I believe it's the AWACS system. Yeah. So let's see. I'm going to deviate from these slides a little bit here. So let me do this. I'm not going to follow those slides dutifully. Let's do the math talk thing for a minute here, because we have a couple people who are more mathematically oriented. I know if we did systems engineering, anytime I hear engineer, I know you're not afraid of math. And I know we had some people doing data analysis and whatever. So let's talk about system dynamics from a mathematical point of view. Not that we're going to start doing all sorts of crazy math, but just so you understand that what we're doing is not a toy, that there's a lot of sophisticated things happening here. So let me just sketch out briefly. We're gonna do this with the software in a minute here, but just for now, just briefly sketch out a simple system dynamics model. So, I want a thicker line. Sorry, I guess it's this one. So there's going to be a bathtub here, and that's a rectangle. And we're going to name it anything we want. I'm just going to name it Y for the moment because I want to do a math talk kind of thing briefly here. So it's a bathtub that's going to fill up with something. We don't know what it is. We don't care what it is. It could be it could be a soft variable, a hard variable, it doesn't matter. That's called the stock. And then we're going to put a pipe and faucet assembly here called a flow. In system dynamics in the software, we represent it like that. Okay, and I'm going to name this flow dy dt. Now, when we're really doing system dynamics modeling later on, we're going to name these things more insightfully. dy dt, that seems mathy and it doesn't tell me a whole lot. And why, what does that mean? But we're going to tidy that up as we go along, but just bear with me for now. So this is a stock, and this is a flow. So we model stocks and flows, okay? But we also model feedback loops. So I'm going to put a telephone wire in here. Okay, and now I've created a circle if you follow the arrows, right? So that's a feedback link making a feedback loop. So notice that the stock and the flow are part of the feedback loop. Okay. And then I'm going to put in a parameter or a constant, which is, think of it as a weight, a mathematical weight that I'm going to use in this model. I'm going to call it alpha, and I'm going to put a telephone wire from alpha to the flow. Okay. Now, you'll see when we do this in the software that when you plop down these iconic things on the screen, what each of those icons is an equation. That doesn't look like an equation, but the equations are hiding underneath the icons, and we will reveal them as we go along. Okay. If you wanted to see the equations, you could do that. You could say, all right, click on this alpha icon and a window will come up and you can define it. You could say alpha equals something like 0.02. So that would be a weight, 2% or 0.02. If you would click on the stock, there would be a window that comes up that it would show you a bunch of stuff, but this window would say, tell me what the initial y sub 0 value is, some number. Could be an equation, but let's say it's a number. So in other words, the software is going to determine how much stuff is in this bathtub, but it doesn't know how much stuff is initially in the tub. You have to tell it. It might be at time 0, y sub 0 is time 0. It might be that there's nothing in the tub, but it doesn't know. You have to tell it. And then if you clicked on this flow icon, a window would pop up, and there's where you would define the ordinary differential equation. And you would say, well, dy dt is equal to alpha times y. So because we stretch these two links here, alpha and y, to the flow, the software is going to say, you've got to use alpha and y in some fashion. You got to combine them in some fashion to make the dy dt equation, to make the ordinary differential equation. The software, don't know how you want them combined, but y and alpha have to be used somehow in that equation, dy dt equals something. Okay. Now, to solve this model, what we would do is run it in the software. So when you would run the model, what you would see is a graph over time with Y in it, and it would look like this. And over here, this value where it starts at time 0 here, that's time 0. 0 with a slash through it. That would be Y sub 0. So that's where it would start. Y sub 0, whatever you told it is the initial amount of stuff in the bathtub. So when it solved the model, it would tell you how much stuff is in that bathtub called Y at every point in time. So as time unfolds here, the software is telling you, Stella is telling you how much stuff is in that bathtub. Now, if you want to do the exact same thing in calculus class, the exact same thing, what you would do is the professor would give you the following on a test: dy dt equals alpha times y, and you would be told, solve that ordinary differential equation. Okay, so we're going to skip all the calculus. So a bunch of calculus would happen here. That is the squiggly line. And what happens is mathematicians over the centuries have devised ways of solving stuff like that. So what you're taught in a calculus class is to recognize, number one, it's an ordinary differential equation. Number two, it is of a particular form. And then you're taught an ordinary differential equation of that form has the following solution. And then you plug it in and do the solution that you've been taught. And if you get it right, you get an A, right? So what would be the solution to this ordinary differential equation? Well, it would be Y sub t equals Y sub 0 times E to the alpha times t. So that's the solution. So as a student, I always thought it was weird that, and nobody could ever explain this to me intuitively, we start with an equation and we end with an equation. Like I always thought when you do an integral, you get an area underneath a curve, right? You get a number. It could be indefinite, so maybe not a number. But you know what I'm saying? Sometimes I thought it's just weird. You start with an equation, you get an equation. The solution to an equation is an equation. I just thought that was weird. Well, really, if you think about it, it's not weird. When you solve a differential equation, we're doing the math talk part now, just so you see what's going on here. You don't have to know the calculus or anything. This solution, this answer tells you how much stuff is in this bathtub Y sub t at every point in time. If you would put this in Excel and put in for t, 1, 2, 3, 4, 5, and it would kick out, alpha is 0.02, right? T is 1, 2, 3, 4, 5. E is that magic number. We'll talk later in the course. What is E? 2.718, right? And Y sub 0 is this number here. Whatever you said is initially in the tub. You plug all that into Excel and, give it T equals 1, 2, 3, 4, 5, a column of T's, and then graph it. Guess what? You get this. They're identical. Same thing. Okay. So that's what we're doing mathematically. They're not really identical. This is only over here. This guy is only this one here. The simulated solution is only approximate. And this is exact. So it can be a very close approximation, but it's not identical. The reason is when you put E in here, if you will, the machine would be taking infinitesimally small steps, and a digital computer cannot take infinitesimally small steps. So that's why it's an approximation. But it's a very good approximation. Okay. But otherwise, it's the same thing. Okay. When you do all this integral stuff that we've skipped here, this calculus stuff, that's what's happening over here. This bathtub is filling up with whatever y is. It's accumulating. It's summing up. Think about, have you, I know Ashley, as an engineer, you probably had calculus, right?
I did.
So yeah, okay. So what's the symbol for an integral right here? This thing right here, right? What letter of the alphabet is that?
Been a while.
It's just in that letter of the alphabet. What does it look like? You don't need to, kindergartners know what A, B, C, D, E, F. It's
Like a sigma?
well, sigma, but it's an S.
Yeah.
So an integral sign in calculus is just an S. It's an S that means sum up, add up, accumulate. So you're accumulating, the bathtub is filling up, it's adding up, it's accumulating, it's summing up whatever's flowing into it. Okay, that's why, and when you make a smooth S like this for in calculus class, it means it's taking infinitesimally small steps here in the limit. So it's a continuous smooth S. If it's in discrete time, the S is like this. Means the same thing, add up, but now you're not taking infinitesimally small steps. So the computer is doing this because it can't take infinitesimally small steps. And theoretically, with this in here, it's taking really infinitesimally small steps. So it's a smooth S. In both cases, you're adding up the flows. And when you do that, when you integrate, you're creating dynamics. So dynamics occur when flows accumulate in stocks. Nature integrates. That's what causes change over time. That's what causes dynamics. Flows accumulating in bathtubs, or if we had an outflow, decumulating, negative accumulating, it's flowing out. The tub could be draining, right? You see?
Yeah.
So we're really doing at one, depending on how you want to, and now we don't tell the fifth graders this, right? They don't need to know that. Someday they'll know that, but they don't need to, but that's what they're doing. They're doing this stuff right here. But it looks like this. And we don't have to name it Y. We could say inventory or population or morale or whatever we want to put in there. And this could be the change in population, net birth rate, or a net production over sales, or change in morale, whatever concept we wanted to model here. So what happens is system dynamics, if you want to think about it in terms of math talk, we're doing this heavy duty math stuff, but the brain power is shifted away from trying to remember, what's the derivative of sine is cosine and all that stuff and polar coordinates and whatever. You don't have to focus on that. You're instead focusing on conceptualizing the model. What's important? What should be inside of my fence? What do I want to include in my explanation for whatever problem is occurring? So it shifts the brain power to other stuff. And the mathematical gymnastics is behind the scenes in the software. Okay. So that's another way of thinking about, what is system dynamics. Okay, so let's see, what else was I talking about here? I was talking about redesigning the airplane. I think that's a good way of thinking about it. So if you talk to an admiral, a general, a CEO, C-suite executives, somebody in a position of authority, you're trying, the mayor, the governor, or more likely their staff. When I've done public sector stuff, it's the member of Congress. They give you the deer in the headlights look, and then what's the red curve about again, Mike? And then you talk to the staff and they get it. And the staff says, we'll explain it to the congressman so-and-so or whatever. But, for most people, you don't want to do the math talk thing, right? If you got somebody who's into that stuff, you show them the differential equation, they love that. Their eyes light up, ooh, But most people no good. Most people don't want to hear about the math stuff and whatever. That's not their thing. The higher up in the food chain, the less and less they want to know about that stuff, it seems like. And the leadership thing, yeah, they get that as a general concept. Leaders are systems thinkers, and this helps you be a better systems thinker. Okay, cool. But really, the idea that resonates with most people when you say, what is system dynamics, is we have a complex system, the national healthcare system, poverty, income distribution, the national tax code, climate change, sustainability, stuff like that. We have complex systems that are not behaving well, and we would like to redesign them so that they behave better. Okay, we're trying to redesign the airplane. Okay, so to do that, we have to understand how the structure of the system, the current structure, causes its behavior, and we map out the current structure with stocks and flows and feedback loops and limiting factors. And then we try to redesign that structure so that the complex system behaves better. Okay. This also helps policymakers think through the implications of their own knowledge base. So think about it. If you're going to work with others on a system dynamics intervention, the people you're going to work with are typically not people right out of school in the mailroom who don't know anything yet. They're in no position to make any decisions, and they don't know enough to make decisions anyway, right? You're generally dealing with people fairly high up in the organization, right? So they typically have really good mental models, knowledge bases about how the complex system works. If you're working on the healthcare system and working with healthcare experts, they know a lot about the healthcare system, right? They've probably written books about it. So, so you're not going to tell them more about the healthcare system than they know, or military intelligence or whatever. Ashley would know, her toenail clippings know more about it than I do, right? But the question is, does her unaided mental model of that complex system, about which she knows a lot, is she able to mentally simulate it accurately? Or can we map it out and let the machine trace through the implications of her own knowledge base? So to get policymakers, decision makers, high-level folks who know a lot, to get them, the idea is to get them to give you what they know relevant to the problem at hand. And if there's several people in the room, they might not agree. So there's techniques for getting them to reach a consensus, and then let the machine mercilessly trace through the implications of their own knowledge base. And that often is insightful. First of all, they think it's their model, not your model, because it's their stuff in there. And they often can't believe it when what they think is going to happen based on their own knowledge base in the model doesn't happen. Because the machine mercilessly traces through whatever you tell it, right? And if people are signing off and saying, yeah, that's how I think it works, they can't very well disagree with the simulation, right? So one time I was asked to give a talk at the White House back in the 1990s. Al Gore was asked to give, he was vice president, he was asked to give the commencement address at MIT. And he only mentioned one thing from MIT in his address, and that was system dynamics. And he had spent half a day with Forrester and Sturman prior to giving the address. Now, remember, he's into climate change and all that, so he thought system dynamics was really important. And so then he asked that his staff be briefed on system dynamics down at the White House. I don't know why they asked me to go, but I was asked to go do it. So I did. I wielded all. Let's put this way, I was given 1 hour, 45 minutes for my talk, and 15 minutes for Q&A. And we were on a tight schedule. They kept kept to that schedule very strictly. So I go through all my gee whiz stuff, stocks, flows, feedback, all that stuff. And now we're at the Q&A point. And clearly the head dude in the room Al Gore was not there. It was his staffers, but clearly this person was, without saying it, clearly he's in charge, right? Hand goes right up and he's like, well, professor, we could have any one of a number of professors or consultants come here to the White House and tell us about their modeling technique. And you have stocks and flows and feedback loops. Other people have different features of their software and what have you. And he literally says, quite frankly, it doesn't really move me very much. So at this point, I'm feeling quite bad because I gave him my best stuff. I don't got nothing else to give him. I gave him my best stuff, right? So I'm thinking, is there can I point to Haley's Comet and then run out the side door and never be seen again at this point, But then the guy says to me, but there's one thing you said, which I think is very important. And if System Dynamics can do this, we really got something here. So now at this point, I'm all ears. Please save me. Please, God, have this man save me. And he said, what do you think happens at the White House when there's a crisis? The president says, get the 10 foremost experts in the world on this thing into a room and have them tell me what the hell to do. And he goes, geez. He goes, this is in the 90s. He goes, the Blue Ribbon Task Force on Social Security gave us like 3 different proposals. These guys couldn't agree. He said that at the time, the global warming people can't even agree there is global warming in their reports. He says the president tears his hair out trying to figure out what to do. And he said, Radzicki, you've said that System Dynamics can be used to help experts and stakeholders reach a consensus. He says, my God, if you can do that, this System Dynamics thing is something we could really use at the White House. And pretty much my time was up at that point. I bowed and I slid out of the room thinking, okay, it wasn't a total loss. But think about it. You have a bunch of people in the room, C-suite executives, policymakers, generals, admirals, whatever, right? And they all know a lot. These people all have egos. And they're telling you how the system works, at least from their point of view. And you're the modeler, you're trying to filter out the nonsense from what you can use to build the model. And you're rolling back to them and saying, am I getting this right? Tell me if I'm wrong. Is this okay? Partial model testing. Let's look at this in isolation. If I do this, this should happen, right? Okay, good. We're cool. All right. If they're going to fight with one another, and half the time they don't, and half the time they do. And if they're in the room and not agreeing on like, what's the problem or how do things work, you say, all right, where can we all agree? Let's look over here. The widget goes here, then it goes here, then it goes to the customer, right? Who disagrees with that? Nobody. We move on. Okay. Here's how I modeled expectations of whatever. Here's some data. It kind of looks like the data. Does anybody object? Hearing none, we move on. And you find out that, 90% of the model, everybody agrees on. It's just that last 10%. Okay, then we got something we can work on here. Either we do more research and find out, Sally's right and Johnny's wrong, or we run the model both ways, Sally's way and Johnny's way. Every time we try something, we run it this way and that way. You know what I found? It almost never matters. The curves look almost identical because it's not a leverage point in the system. So you tell Johnny and Sally, why are you bickering about this? It doesn't matter. It's irrelevant. You might get brownie points or something, but we don't care. So helping a policymaker reach a consensus is another way of thinking about, what is System Dynamics. Redesigning the airplane, reaching a consensus on what to do to redesign the airplane. Okay, how are we doing? Is everybody bored out of their skull, or are we doing okay here? Where am I going? Again, my cursor's gone somewhere to the moon or something. Here we go.
I had a quick question too, just on everything you said so far. You kind of touched on good models and bad models.
Okay.
And we had talked before about, there are some models that just don't really give you any insight, and then there's some models that do. So,
yes.
So just so I can kind of wrap my head around the concept of what constitutes a good and a bad model, could you give some examples of each one of what you would consider a good and bad model that you've seen?
Absolutely. So I guess I would say the way I would frame it is, bad modeling, I don't know if I would go there, but a bad model would be a model created by a novice that has errors in it. I guess that would constitute a bad model, poor model. So they haven't gotten something. Their equations are not dimensionally correct. We got steady state error and we shouldn't have it. There's first order control that's necessary because we got negative people and we shouldn't have, whatever. There's just problems like that. An intermediate level modeler will typically, I'm generalizing here, but sort of trying to find a template, but an intermediate level modeler will typically build a model that is technically correct. There are no errors. There's, all the boxes have been checked, right, for the technical stuff. And it doesn't really tell you anything that you didn't really know already. Like, something is growing, and if you make this parameter bigger, it grows faster. If you make it smaller, it grows more slowly. Well, you really didn't need a computer model to tell you that. If I get a higher rate of return on my 401k, I have more money later. And if I have a lower rate of return, I have less money. Yes, but did you really need a model to tell you that? Now, the model might be useful to give you some idea of the magnitude of something like that. So, okay, but it's just not terribly insightful. The veteran or expert modeler, I guess you would say, will build a model that's technically correct and insightful. It tells you something that you wouldn't know without the model. You've got to run the model and think through a simulation run to decipher what happened, because there's all these interacting stocks and flows and feedback loops and nonlinear relationships and shifting feedback loop dominance and what have you that's going on. There's no way you could think it through, that a human being can think it through, right? And then you have something, then you need the model to run scenarios and help you think through things. And that would be the best. The highest skill is when you're in that room with all of the highfalutin folks, and they're telling you sincerely, trying to tell you how the system works from their vantage point anyway. And, you have to decipher what they're saying because there's a free-flowing thing going on, and you're trying to remember stuff and take notes and whatever, and then go back and build a model from what you heard.
Right.
It's hard to do. That's you gotta, you have to have a lot of experience, to pull that one off. It's tough, right? But that would be the highest level. So that's even maybe the super advanced level is the ability to do that. But somebody who can't necessarily work the room like that, they're not experienced enough or whatever, but can build a model that before you hit the go button, you say, what's it going to do? And you say, I don't know. And it's technically correct. Then I think that's the what I would call sort of the expert level. And we certainly don't want models, a bad model with just errors in, right? And you don't want folks running around saying, oh, system dynamics, look at this. And they show off these really crummy models that have mistakes in them. It's like, please don't show your work yet. And you give us a bad name, So.
Has the systems dynamics community started looking at the implications of AI on models yet? Is that a conversation that's being had?
In the old days, that's a great question. In the old days, with Chat GPT and all that stuff that's going on now. In the old days, a bunch of doctoral students tried to look at that. And when I say the old days, I'm talking 30, 40 years ago when I first came into the field. And Forrester would always say, every year we got a doctoral student who wanders over to the AI people. It was Marvin Minsky or whatever at MIT at that time. And wants to, integrate artificial intelligence with system dynamics. And they come back all dejected. And so that was an old, that concept, that idea is an old one. And it didn't get very far. A few people wrote some papers back in the day. I can dimly remember. Today, though, things have changed a great deal over the years. And so there are people now who have been just at the recent System Dynamics conference, talked about how one might use Chat GPT, for example, to write better equations and help conceptualize the model. rather than talking to a room full of admirals and generals or CEOs or something, you talk to ChatGPT and say, fan out and bring me back some ideas about global warming or whatever the case may be. So it's being discussed. I don't think we have an answer yet as to exactly how best to use it to enhance what we're doing. I can tell you what Jay Forrester felt. And he would say, even if you, he would always say, this is back in the day, he would say, he didn't think the information base was big enough to pull that off. Now, he wasn't thinking of the web and scraping the web and all that stuff. So big data. So if he were alive today, I'm not sure what he would say, but he didn't think you could do it. But then he would say, even if you could do it, it misses the point of system dynamics. The point of system dynamics is to, redesign the airplane, but to give you insights. And you don't get the insights from pressing a button for the, Chat GPT, what do they call them, app or whatever, I forget what they're called. These add-on things somebody made for system dynamics and Stella, and it just builds the Stella model for you. And it returns the Stella model. Here you go. Well, you didn't learn anything from the struggle to understand, what's important, what's not, what are the important feedback loops and all that stuff. And Jay wrote a very famous memo that we reproduced in the System Dynamics Review. And it was titled, the model versus a modeling process. And he was alarmed that people were building system dynamics models as works of art. Look at my model, this brilliant model, this thing I can point to and reproduce and bow to and whatever. And he said, that's wrong and that's bad. It's the modeling process that generates the value. It's the struggle to understand what structure is causing the problematic behavior of the system. And that struggle gives you the insights. So I think he would say, just pressing a button and having AI build your model defeats that purpose. Maybe the AI engine learns from it, but the humans don't. And he was also very pessimistic. Like I said, he didn't see the latest, greatest stuff, but he was pessimistic that you could even do it. But anyway, but people are looking at it, of course, as you might guess.
Interesting. Yeah. All right. Thank you.
Yeah, no problem. Nayla, how are you doing? You have your hand up? Virtual hand?
I had a question. Yeah. Oh, yeah. And it's Najla. You say the J.
Najla. Sorry. Yeah.
Yeah, that's okay. Like I tell people, Naj rhymes with beige. So it's Najla, like Beigela.
Oh, that's a good way to, yeah.
Yeah. It's a good way for English speakers to learn it, or French, I suppose. But anyway, so you had mentioned that there were like some problems that some people, when they start to study system dynamics, and they're just like, oh, it's like, if you have a hammer, everything looks like a nail. And they're just like, oh, this is the answer to everything.
Yeah.
I'm really curious. Yeah, I'm really curious as to how how that is framed as far as, in your perspective, how you delineate what's a good rule, if any, are there several, for delineating what are the problems that are good for system dynamics, and as opposed to the ones that aren't.
Yeah. Well, we'll talk about some of that as we go along, but Jay Forrester, when he created System Dynamics, did it for corporate modeling. And it, of course, expanded where you can kind of model anything that moves, right? But he would say the shop floor level, where you're trying to model the movement on the assembly line and optimize the movement of the arm of the crane so it doesn't move as much.
Industrial engineering.
Yeah, right. That's too close. That's not a system dynamic. You could do it, but that's not really what system dynamics is designed for. You say stepping back from that to the CEO level, he thought was still a little too close. He said it was the investment banker level. And he said, think about being in a helicopter flying, or an airplane flying above the earth, and you look down and you see the little patches of farmland and stuff. Each of those would be kind of a sector of your model. So you're seeing how the sectors, interact and stuff. The farmland is abutting and whatever. that it's the investment banker level. You're far enough away. You're not worried about the details of the drying time of machine 3 or the crane arm or whatever. And even the CEO level is a little too close. You're stepping back, sort of hovering above the system, looking down. It's a top-down approach. It's an aggregated approach. So when we model a stock of population, the bathtub has people in it, people are different, right? There's men, there's women, there's young, there's old, there's rich, there's poor, there's sick, there's healthy, there's, whatever. And that stock just has people in it. Now, if you want to separate men and women, let's say, or whatever you want to do, let's say, pick that, you got to make 2 stocks. Or you got to do there's other gymnastics. We can do co-flows and things, but let's say you want men and women, rich and poor. Well, now you got 4 stocks. Men, women, rich, poor, young, old. Okay, now however many stocks. Well, as you add more and more detail like that, if it's important to the problem, at some point it gets rather clunky to do with system dynamics, because it's not only, you can go from rich to poor and poor to rich. So now you got flows going each way, and you got all sorts of stuff. At some point, it's an agent-based modeling problem. When is that? Hard to say. Give me the exact number of stocks before it's an agent-based problem. Hard to say. But at some point, you're more concerned about the micro level details rather than the big picture level stuff. Because agent-based modeling is a bottom-up approach, system dynamics is a top-down approach, and there's sister techniques. Now, if you're just trying to
model, was the agent-based modeling is something more like an individual perspective, like psychology or those kinds of fields?
Yeah, you could have 100,000 agents, and they could be cars, drivers, people, banks, firms, whatever you define them, molecules, cells, whatever, and they would be given rules. So a cell might be given rules by nature. A person might have rules because they imitate their neighbor and their parents raised them a certain way, or there's cultural norms or whatever. And you load that in, and then you let the cars interact, or the cells interact, or the people interact. And then you sum up the purchases or, whatever you're worried about, and that gives you the aggregate behavior. Whereas with system dynamics, we start with the aggregate behavior of the system and we look down.
Yeah.
So it just depends on what you're trying to do, what questions you're trying to ask and answer. Now, if you're trying to forecast the stock market or whatever you're trying to, you could use system dynamics to do that. I don't think it's the greatest tool for, like, what's the price of Bitcoin going to be, 6 months from now? I would use a neural net or something to do that. You could do it with system dynamics, but it's really not made for that. The system dynamics would give you a why. Why is it going to be whatever the price is? Because you'd model all the whatever's happening there. Whereas a neural net, you would open up the neural net and say, show me. And it would be like, this crazy, all the nodes, and it wouldn't be interpretable by a human, but it would predict better, right? In terms of hitting a number 6 months into the future or something. So again, it depends on what is your problem. A lot of problems you could do it with system dynamics, but really it's not a system dynamics problem, right? So, and I don't know that anybody has written like, here's some hard and fast rules. You could almost have a software program. If you say, here's my problem, and go, or ChatGPT, you should be using linear regression or linear programming or agent-based modeling or data science or neural nets or support vector machines or system dynamics.
Thank you.
Good questions, one and all. So I'm looking at my clock. I got 7:47. Today was more of an organizational meeting, more of a broad, sweeping overview thing. I can give you a couple more things before we go, because I know people probably want to have supper, and the mind can only absorb what the seat can endure, is what's that phrase or whatever, right? But just a couple other things. Let me do this. Let me show you something over here. When we do system dynamics, what we're trying to do is look endogenously or inward for the sources and causes of our problems. So, oh, I got the wrong one. Sorry, beg your pardon. Let me get rid of this one. Let me look at this other one's what I want. So, here's this one here is, I guess, a good example of that. So we're not trying to create a digital twin of the system. We're trying to model a problem a system is experiencing from a systems perspective. So that means we're going to leave stuff out of our model that's in the real world. It might be a very important thing in the real world. It's just not important to the problem. So there's a saying in system dynamics, rookie or newbie modelers ask the question, what can I put into my model? And veteran system dynamics modelers ask the question, what can I leave out of my system dynamics model? So what we do here in this slide I'm showing is you draw a fence. And if something is inside the fence, it is important to the problem statement. So we include it in the model. Everything outside the fence is in the environment. And even if it's an important thing in the real system, it's not going to be part of our model. Now, with a caveat, there are holes in the fence. So stuff can leave from the inside the fence and go to the environment, or it can enter from the environment. So the system can be shocked from the outside. So there's one-way causation. There's no feedback. It's just one way. Something hits the system from the outside, but the system does not feedback and alter the shock. The shock, by definition, is shocking. It's unexpected. Okay, and things can leave the system as well. But otherwise, we have this fence. So we're always asking what's inside the fence and what's outside the fence. Okay, if it's inside the fence, it's not just it's important to the problem statement, but it's part of a feedback system. There are closed loops. Okay, so we're looking for closed loops of cause and effect. We're looking for feedback loops. We're looking for stocks and flows too, but we're looking for feedback loops. So outside the fence here, there's no loops. The system doesn't react and feedback to the shock. But inside, there's loops. There's feedback loops. There's circles. In fact, we have a system dynamics song. No lie, not kidding. You go to the conference, and at the end of the day, when some of these dudes have had a few cervezas, you can get them to sing it. They'll stand up at the bar and sing it. Pretty funny. But the title of the song and the chorus of the song is called Close the Loop. And I may actually...
I've been to several conferences and nobody has sung the song for me. And then that begs the question, is there a dance that goes with the song?
Yeah, well, these guys dance, but I don't know if it's an official dance. Here's George Richardson and Joel Rahn. Actually, that's in Bergen, Norway. I was there doing it. And you can see here's literally the song.
Oh my gosh.
Not making it up. So we're looking for feedback loops, okay, for closed loops of cause and effect. So when I come back over here, let me put a little meat on that bone and show you what I mean. So over here, if you look to the side, can you see, let's see, what do we have here? You see, I put in data points here. Population, I just made this up. Okay, so I just typed in some data. Now I might have, if I would, this is just play data, but if I had gone to, the US Census Bureau or whatever, I could have gotten actual population data. Okay, actually this is change in the population. So one census to the next, how is the US population change, or the population of Massachusetts or Arkansas or Indiana changed, whatever. And I put it in here, over here, and it says population data. So I'm going to graph this over here. And if I simulate it over here, all it did was sum up or add up those numbers. So this graph is exogenously driven or exogenously created from the outside. I was just pushing the system with numbers from the outside. See this cloud over here? That's the hole in the fence. Those numbers are coming in from outside. They're exogenous. They're not part of a feedback system. Okay, so let's say this was very accurate for whatever we were doing, fine. But from a system dynamics perspective, it's crummy. There's no feedback explanation. There's no endogenous explanation for why that's happening. It's exogenous. You're forcing it to happen. It's almost like a tautology. It's so because you define it to be so. On the other hand, here's a simulated population over here. All right. And so this graph here is generated by this model. And look here, I have inside of here, there's an equation. Okay. There's a parameter. This is what I did before. I hand drew it and it was 0.02 and all that. Alpha is 0.02. And I simulated it, but now there's a feedback loop here. There's an endogenous explanation. It's generating this curve endogenously. It's not driving it exogenously. So this would be a legitimate system dynamics feedback closed loop explanation. And this is an exogenous shocking from the outside non-legitimate system dynamics model, even though it was done in system dynamics. Now, let me further confuse you. I got population data here, population simulated here. Delete that. Let me put that on here as well. Okay. And let me just resimulate here. And you can say if the blue line is the actual data and it's driving the model, and my red line I'm saying is the system dynamics model, which is legit or good or better because it has a feedback loop. But the blue line is more truth, accurate, or whatever, better in the real system. You say, well, it might be exogenous, but it's better. But look at this. I just go twirl my little knob here, changing the parameter. I'm manually fitting it to the curve. I could have asked an algorithm to do this lickety split, but I'm just twirling my little knob here. Which one is better? They're essentially identical. Not exactly identical, but pretty close. But one was generated with a feedback loop and endogenously, and one was generated exogenously. The endogenous one would be seen as legitimate by SDers, the exogenous one not. Now, that's a little caveat there. Sometimes we do drive our models with exogenous stuff, but it's not the whole thing like this. That it would be just one piece that is being, so there's a little bit of a caveat there, but this would be trying to get to the point of we're looking for these feedback loops and for endogenous or circular explanations for something. Okay. All right. What's my clock doing here? 7:56, just about done. So I have, what else do I have here? I have some examples. Let me show you, if you bear with me, let me show you one last thing in the off chance you want to get going on your quiz assignment, whatever you want to call it. So I mentioned that we use system dynamics to produce games so others can benefit from our models, even though they didn't participate in their creation. They didn't participate in the struggle, trying to figure out how the structure causes behavior and all that stuff. And yet they're going to be asked to make decisions, hopefully based on the model, to believe the model, to have confidence in the model and what have you. How do you do that? Well, gaming is one way that seems to be an effective tool for helping others understand our models and what have you. So because we had a COVID thing, I built a SIR, which stands for susceptible, infectious, and recovered epidemiological model of a pandemic. So this is one of the things you'll be asked to play around with for the quiz. And I've been working over the last year to try and develop a template so that I can make, because I got a lot of games I want to make, models I want to turn into games, and I want them to be consistent. And of course, every time I have a new idea and I really like it, then I got to go back and revise all my other models because the template has changed a bit, but it's starting to settle down. So this one pretty much follows the template, although not perfectly, but it's pretty good. So there's always going to be a table of contents and a learning objective. And what this is basically saying is you're going to give you some insight into epidemics, pandemics, and whatever, but really it's introducing flight simulators and the idea of, turning a model into a game. I'm not claiming I should be hired by the CDC to create, to be an epidemiologist. That's not what I'm trying to do here. I'm sure there's better, pandemic models than mine. I'm simply using it as an example from recent current events as to how we would build a model and then turn it into a game to give you an idea. So then my template has background information. And so in this case, we're going to talk about, well, what do we mean by an SIR model and a pandemic and epidemic and stuff like that. I'll let you read all this stuff for the assignment, okay? But remember, we always start with a problem statement. We model problems from a systems perspective, and we turn that problem statement into a reference mode, which is the dynamic behavior that is a picture of the problem. And that's the behavior we would like our model to mimic, its base run to mimic. And then we also ideally would specify what we mean by solved or better or whatever, right? And we would show that in terms of the reference mode. So over here, I have some graphs I fetched from the internet. And you'll notice here that this is the infection rate. That would be a flow without protective measures and then with protective measures. So basically, you might have remembered during COVID that we talked a lot about flattening the curve, right? Because they didn't want to overwhelm the hospitals with COVID patients, right? Flattening the curve. So this is an example of flattening the curve. So this would be the problematic reference mode. That's the problem. And then better or solved or whatever is flattening the curve, so you don't overwhelm the hospitals. And then over here are some graphs, both with actual data with the kinds of variables you'll see in my model. Okay, so that's why I showed this. All right, so we want, the model should do this in its base run, and then we want to try and make it do this with redesigning the airplane with policy changes. All right, structure causes behavior, right? And then to change the behavior, you have to redesign the airplane, change the model structure or the system structure. So we talk about, well, what do we mean by structure? Stocks and flows and feedback loops and stuff like that. Okay, so again, you can read that on your own. And then let's look more specifically at the model. Okay, so now we have susceptible people. They don't have it, but they could get the disease. Infectious people and recovered people. Those are the stocks. The flows, there's an infection rate, a recovery rate, and a death rate. So some diseases, you don't get a death rate. You don't die from it. Some diseases, you don't recover from. It just depends on the disease. So not all diseases are the same, right? So in this case, I put in a death rate and a mortality fraction and a recovery fraction, okay? There's an average duration of the thing. How long do you have it before you're recovered, if you recover? And then over here, this is going to be a nonlinear relationship here because we have to have stocks interacting with one another. And as soon as stocks mathematically interact, you have a nonlinear model. But it has to happen. In order for somebody to get the disease, an infected person has to interact with a non-infected person, a susceptible person. In order to hear the rumor, the person who hasn't heard the rumor has to interact with the person who has heard the rumor. And then they have to pass the rumor. They have to tell them, not keep it as a secret. So there's a contact rate here. What's the chance that we run into one another? And then if we run into one another, there's a chance that I pass it from me to you. And different diseases require different levels of interaction in order to pass the disease. So you can set it up for any kind of disease that you want. We also put in not only other factors, but policy space. This is kind of both. At the time of COVID, they were talking about closing the airports and not letting people in and out of the country, not just the United States, but other nations were doing this. because people were coming in with it, not knowing it, and adding to the infectious population. And a policy change would be to say no in-migration during the pandemic. We had some social distancing masking policy space in here. So as the infection rate starts to trend north and people start to perceive it, that, oh boy, there's a problem here, it's a rising problem, then they can take measures to combat that. So I didn't make it specifically social distancing and masking, but that's what I mean by this, that as they perceive it to be not only there, but a rising problem, the trend is going up, like, wow, there's a relationship in here that says start taking measures to mask and social distance to stop it, right? But then I also put in some effects of social media, the public's belief and the necessity for social distancing. Do masks really work unless it's N95? Fauci said wear a mask, then 2 masks and 3 masks and 1 mask, and then he's at a ball game without a mask. Do I really believe it? So you can put some suspicion in here as the public's understanding as to the importance of doing this or not. And you can adjust that to see what effects that would have. You can try a quarantine policy. So now we're adding policy space. If you're infectious, some or all of the people, you can change the fraction, are going to be quarantined. Okay. And then they recover. You can vaccinate people. So if they're susceptible, you can vaccinate everybody, nobody, or any fraction in between. And then, of course, there is some recovery time. But again, with a disease like COVID or the flu or something, just because you had it doesn't mean you can't get it again. And some people have had it 2 or 3 times. Other diseases, once you've had it, you really don't get it again. Okay, so that's the structure of the model.
Did you do that whole thing in Stella with the little notes and stuff?
Yeah.
Or did you add the note thing later and do screenshots?
No, it's Stella Architect.
Okay.
Yeah. Which is one of the reasons I use Stella. So now that we know the model structure, and by the way, I could have shown you the equations and stuff, but I made this for the beginners. I didn't make it for, let's look at the details of epidemiology. So I could have allowed the player of the game to do a deeper dive into the equations and whatever the structure, but I didn't do that in this case. Then once you know the structure, what about the behavior? So you go here in my template format, and it gives you things to do for the base run and then experiments that you could run. Okay, and then after a while, you run your own experiments, multiple experiments or whatever, and compare. You can set up different diseases, whatever. So you got all sorts of things I suggest you could do. And then you go to the cockpit, or excuse me, the setup board. And so you can specify what kind of disease, how fatal is it? Not at all the way to everybody dies. Do people lose immunity or not? Some probability, how infectious is it? Do you just have to look at somebody and it passes, or do you really have to, interact, on the wrestling mat or something before it passes? How much are people out and about? How much contact is there? Do you live in remote Alaska and you're not really running into people, or you're riding the subway in Tokyo every day, or whatever the case may be? Then how long is it? So you can set up the disease any way you want. The in-migration policy over here, the base run allows in-migration. Nobody's being quarantined at the beginning. Nobody's being vaccinated. And there is, well, you got to turn the switch on, but then there is no suspicion of social distancing or, honor my fellow man and woman policies, or whatever you want to call it. But you can change all that. So you go to the cockpit, and now over here is the comparative. That's where you're going to try and flatten the curve. Okay, so we'll run the model once to get the base run. And here you have that spike. And if you don't remember, you go over here. That's what the yellow thing is what we just generated here, right? And then you're going to do a lot of runs. So we'll call that one the base run. Okay, So we know that's our standard against which we're going to test things. Okay. So then you go back to the setup, and I wouldn't change the disease, leave the disease be. But what do you want to try here? You want to try an immigration policy? What do you want? Any suggestions? What do you want to do? We're going to leave suspicion off.
Let's increase migration because people are trying to come home early from vacation because there's a COVID outbreak in Europe in the summer.
Okay, so let's really aggressively do it. I mean, I don't know what okay. And we'll run it. Okay. So that was more immigration. Okay, so certainly didn't flatten the curve, but it didn't do all that much to, I mean, it's not terribly worse. Peaks sooner, a little bit higher, but okay. Other thoughts? Now, for the homework, you're going to do it. So I don't want to do it all here, but just to give you an idea of. So we'll do
increase
2 more.
social distancing.
One thing at a time at the
Oh
beginning,
shoot!
because if you make multiple changes, you don't know the effects.
You won't know
of
what
it.
happened. Okay, I know how that
So
works.
you want social distancing on
Yes.
with no suspicion.
What do you mean when there's suspicion?
Well, some of the effect is damp because some people aren't believing the Fauci saying to wear a mask.
No, they're believers. They're going to do it.
All right. So 100%, we'll leave it there and we switch it on now.
Yeah.
Okay. Very different. Certainly is flatter and the peak is pushed out more. Cool. So that would be,
Social distancing, believers, 100%.
just say 100%. If you make the names too long, it gets you. But you get the idea. So the question is, what policy or combination of policies seem to work the best? But then, and I'll wrap it up with this because we're over time here. You're always asking as a system dynamicist, because you don't want to do this is a work of art that I'm going to now frame and put on my wall and bow to. Can a real policymaker pull off whatever these things that we're doing here? When you go here, these things, can you pull them off? Can somebody who doesn't do system dynamics, but does public health or is a politician or whatever and says, what the hell am I supposed to do? Can they pull this off? Vaccination policy. Whoa, when I made it 100%. Well, can you get 100% people vaccinated? You can say aspirationally, if you got 100%, but you might say, look, realistically, yeah, we'd like to have 100%. Let's see if we can get 30%. And let's see what that does. And can you pull that off? President, so-and-so, governor, so-and-so, mayor, so-and-so, whatever, right? Or quarantining. Can you pull it off? Oh, quarantine. Well, where are you going to put them? WPI actually put students in a hotel when they had it. They did quarantine. But I mean, can you actually, if you don't have a hotel to put them in, well, how are you going to quarantine them? Oh, it works in a model, but can you actually pull it off? Right. And how do you pull it off? So that's part of it. Because Forrester would say, otherwise, it's the theory of bridge building rather than you're building the bridge. Right. We're not just doing a theory of bridge building. We want to get across the river. Right. So can you pull it off? So that should always be in the back of your mind as well because you're going to be, again, Ashley, you work with admirals. They're not going to care about this. They're going to say, tell me what to do and back it up with something solid. Right. And don't give me a bunch of stuff about Runge-Kutta methods or whatever. I want tell me what the hell to do here. Right. So
in my world, Mike, we call that owner compliance.
Yeah. Yeah. I mean, it's a human trait. And it's not that the top people are dumb. I mean, they wouldn't have got that far, presumably because they're idiots. They have something going for them, presumably, unless they're the boss's son or daughter or something. I don't know. But I mean, they're usually not stupid. They don't have the time to do a deep dive and learn system dynamics or something. So you got to come with a compelling story and B, stuff that they can actually pull off. Levers they can really pull, not some theoretical lever that they're like, well, you haven't given me anything. Raise morale. Well, how do I do that? Tell me what to do. Well, I don't know. Just the model says raise morale. Well, So anyways, these are the sorts of things that we have to bear in mind. So we're not just doing academic egghead stuff, but have a tool that we can really use to change actual complex systems. Right. All right. Enough of me. I could talk till the cows come home. Actually, I got to go out in the barn now and finish cutting my insulation because that cement truck's going to be at my house tomorrow morning. So,
So you're gonna send that stuff to me and then
yeah, let me stop sharing. Okay, here we're at. Sure. Yeah. I got to send a couple of them out. So I'll figure out, I got to,
then Najla and
figure
Ashley
out
can
how
do
to,
through your software online on campus.
yeah, I have to figure out what I have to like PDF or whatever.
No emergency. I'm not gonna be able to sit down and do
and
it.
send
till
it. But
Friday.
I'm happy to do that. That's not a problem. It's just that,
Do it later. I'm not gonna get to it till Friday.
right. Yeah. But I just have to figure out first what to do before I do it. Like what's going to work. I think I can PDF it and maybe the links will remain. I'm not 100%
Yeah.
sure. I might have to include the PDF files along with the PDF of the syllabus or something. I have to figure it out, but I'll
Okay.
So before we go, hopefully this is good, this format. Once a week, couple hours on a Monday. There's stuff to do in between. There's stuff to do that's assigned. It's not overwhelming, but there's also other stuff you can read or whatever if you're interested in a deeper dive on something. Most people say this is fine. There's no need to do this twice a week. Enough already.
Mondays works great for me, actually.
Okay.
Because I'm kind of mentally recovered from my previous week because I don't work on Mondays. So it works really well for me.
Okay, so is that okay with everyone? And Mondays are,
Yeah, Mondays work well for me as well.
okay.
Yeah, same.
Najla, okay, it's okay. All right. So we'll meet then next week at 6 o'clock on Monday. Is that Labor Day?
It is Labor Day.
Do you want to meet on Labor Day or not? It doesn't matter to me. I don't particularly do anything unusual on Labor Day. To me, it's just a Monday. But I don't care. If we meet, we meet. If not,
It works for me. Works for me.
So you want to meet? It's you.
Yeah.
Yes. Okay. All right. So then next Monday, 6 o'clock. When I get a chance and figure out what to PDF or whatever, I'll do that. Send it out. The recording. I will put the recording on Canvas, but I also will put it somewhere. I'll have to figure out on a YouTube. I think I have a YouTube channel I can stash stuff. So let me
And then
stick it.
just send me the link to it.
Yeah.
Make it
I think
private
that's
and send me the link.
the YouTube channel is probably the best way to do that. Other bureaucratic anything?
I was just gonna suggest that for sharing the course syllabus and assignments with Suzanne, you might put that in like a online file rather than sending lots of documents back and forth.
Oh, you mean like Google Drive or something?
Yeah,
Yeah.
some kind of a folder. I would do that personally.
Yeah. You're right. Yeah, I hadn't thought carefully about that, but yeah, that's rather than choking the email and whatever. Yeah. Okay.
Yeah, because I use Google. You can just share the whole file with me and keep it on your Google account and then just share it just with me.
Right. Yeah. I think I have a System Dynamics, WPI System Dynamics YouTube channel and Google Drive or something that I can just keep it separate from all the other nonsense that I got going on. Yeah. Okay. So that's cool. And anything else or?
In addition to the quizzes, is there going to be any like final project where we build our own model or something along those lines?
Not unless you want to. I don't require it. Normally, I'm doing this in the evening for people who are working for like Electric Boat, and they're like overwhelmed at work anyway. So they're like, no, this is fine. But kind of like those who say I can use this at work, take it and run with it, and actually use it at work. and make it do a project, and other people are like, yeah, I'm good. It's fine. Interesting, but I move on. So I don't like to beat on, like the beating should be voluntary, not mandatory. So if you want to do a project and you want me to look at it or something, happy to do that, but I won't make it mandatory. And that
Okay.
seems to work the best. So, in your a world of, in military intelligence or training the cadet, I do have a, did I tell you about this leadership subordinate model that we did with the ROTC?
I keep asking to see that.
Okay, so we can, that might be of interest to you, and you can do something that we're going way over time today, but so there are things that would perhaps be of interest to you in your career and whatever that we've already done, or we can look at and you can goof around with or whatever outside of the main drag here. Happy to do that, depending on your interest and time availability and all that good stuff. So just let me know, and you can email me privately or what, and you're on campus, so I can see you face to face in my office if we can't do that from Arkansas or Indiana, but we can certainly do it on campus. So maybe we'll go have a coffee or something if you want to discuss a project or a model or whatever. So
Okay, great.
okay, all right. Well, hope you guys had fun. I did.
Same bat time, same bat channel next week.
Yeah. Okay. See you
Thanks,
all.
Mike.
Thank you.
Bye.
Thank you.
Bye.
Bye.